Hello and welcome to using data analysis techniques to answer research questions with two variables. In this case, we're going to be looking at variables that are, I'm just going to skip ahead, one categorical and one measurement. Now before we do that, I want to mention or remind you that we're going to be looking at these processes. So process A is exploration, practical significance, and statistical inference. When we look, now we've already covered two categorical variables, two measurement variables. When we look at one categorical and one measurement variable, when we're analyzing them, what we're going to be doing is, and think about this for a second, comparing means. One categorical and one measurement. Keywords, compare means, as I said. When we explore, we compare means, medians, standard deviations, etc. Visually, paneled histogram, comparison, box plot. Practical significance will be raw difference, percent difference, Cohen's d, and the hypothesis test will look like so. Two independent means when the categorical variable has two categories. So for example, are Canadian males taller than Canadian females? The null hypothesis looks like this. The mean of males equals the mean of females. We assume we start off with a null hypothesis that they're the same, or that the difference between them is 0. Another option is when we have more than two categories. When we have more than two categories, then we do what's called an analysis of variance, ANOVA test. And it's very similar to comparison of means, but not in the SPSS workings. But conceptually it's the same. Instead of having two means here, we have 4, or 3, or 5, or 6, as it may be. And in this case, the question I want to ask is, are Canadians who prefer Conservative Party wealthier than Canadians who support the NDP, Liberals, or Green Party? So the mean here is the mean income or the mean assets of these Canadians. Let's look at comparison of means, which means we have one categorical variable with two categories and one measurement variable. And we're going to open up the survey stat 1013 dataset, which I have here on the right side of the screen. There's the variable view, and here's the data view. Question is, do Canadians born outside of Canada have more siblings than those born in Canada? So that's birthplace. Well, here I call it born in Canada. And I take a look. I have yes, no. Are you born in Canada? So that's birthplace. And number of siblings. So num siblings is another variable, and it's not a categorical, it's a measurement variable. So let's explore it. What do we do? Well, analyze, compare means. So let's look at how this works. The independent variable in this case is going to be, were you born in Canada? So that is were you born in Canada goes here, independent, and the number of siblings goes in the dependent list. Now in options you can select whatever statistics you would like, and I always like to add in median and move it up here. So you have mean, median, standard deviation, and the number of cases in each group is important too. But there's a whole series that you can have here. And we continue. Click OK. And let's take a look at the output, which we have on the left side of the screen. And this is the numerical output that you're going to get. So 1.8, 2.26, and it's the same numbers we have here. Visually, we're going to go to the graphs. We're going to produce comparison box plots, which you've done before. Simple. Again, were you born in Canada goes in the category axis. Number of siblings is the variable we're interested in comparing. And finally, histogram. We do a paneled histogram. Were you born in Canada by rows, and number of siblings is the variable we're interested in. And so this is the same output we have here. When we take a look visually, these look very similar. And same thing on the box plot. We see some differences, but it's not a huge difference. When we compare means, and medians are the same, but we compare means are very different. So next we calculate practical significance. We look at the raw difference, percent difference, Cohen's d. So I'll leave you to look those calculations up. They're pretty straightforward. And hypothesis testing. Hypothesis testing is through the same. We're going to look at compare means and the independent samples t-test. Independent samples basically means that when we chose the two groups, or that Canadian-born versus non-Canadian-born groups are not related in some way. So the grouping variable here is going to be were you born in Canada, and the only trick you have to worry about when number of siblings will put in is a test variable is how were they coded. Well, how were they coded? Well, we don't know. I have to cancel out of this, go back to the data set, and take a look. Born in Canada, 1 was yes, 2 was no. So it's not 0, 1, it's 1, 2. Independent samples t-test. Again, were you born in Canada goes here, number of sibling goes here, and we define groups. One of the groups is group 1, the other group is group 2. And now we have the t-test, so it's the same one as we have here. And the only thing you have to worry about here is the significance, two-tailed significance. This here is another test, hypothesis test for the equality of variances, which is important. Now the Excel calculator is going to allow us to calculate the 95 confidence interval for the difference. So here, the raw difference. So this is very important. That is what we're going to be calculating the confidence interval for. And in this case, the raw difference, if you remember here, back here, the raw difference was those not born in Canada have 0.46, so almost half of a sibling more. And here what I find is that the lower bound is 0.22, so almost a quarter, up to almost 3/4. So that's if I took this sample and I said we want to generalize it to a population. In this case, it would be a population of friends of HIM students and family of HIM students. What I would expect to find in the population is that non-Canadian born Canadians have between 0.22 and 0.71 siblings more than Canadian born Canadians. Here's the final statement. Take a minute to think about it and read it. And now we can move on to the ANOVA. In this case, the ANOVA basically is looking at more than two categories. So we have 50 Torontonians were asked to define their education status, full-time, part-time, or non-student, and then the amount they spent on junk food per week. I would expect full-time students will spend more on junk food as they are in a rush and needing to grab a snack. So do students who have a busier educational status spend more on junk food? It's a research question. We have a dependent variable, which is dollar spent measurement, and an independent variable, which has more than two categories. And we're going to explore. How we're going to explore? Well, we're going to do the same thing in terms of numerically and visually that we did with the other one, where we only had two categories. There's really no difference. So we do means. Amount spent on education is dependent. That's the measurement variable, and the categorical variable. And again, options, we're going to add in the median here. I think it's very useful. Okay. And we're going to do graphs. We're going to take a look at the box plot again. And now amount spent on education is variable, education status, the category axis, that's easy. Now this time I'm going to think ahead and look at the coding for education status. We have 1, 2, and 3. And I'm going to look at that paneling of histograms. Amount spent is variable, education status goes here. Sorry, we need that for histograms. And so this is what our histogram looks like, and the same one as we have here. Our box plot is here, so we can see clearly that there's differences between these groups. And ANOVA works on, the box plot is the best picture for an ANOVA because we look at the amount of variation within the groups compared to the amount of variation between the groups. That's what it's actually looking at. So there's an expectation of them being similar, and if they're not similar, then we get a low p-value. So this number, you see I've changed it a little bit just to make it. And we look at full-time students spend 2.18 times more than non-students. So that's when we look at this number compared to this number. This is a raw difference. This is Cohen's D1 standard deviation. So we see there's a huge difference between full-time students and non-students, and then part-time students are somewhere in the middle, which is very nice actually for analysis. The hypothesis test. Scroll down here. Can go back to the data set. So the hypothesis test we do through, again, through compare means and a one-way ANOVA. So one-way ANOVA goes here. Amount spent on food is the dependent, list of dependent variables, and education status is the factor. Now we don't worry about these yet. Click OK. And we get the same output as we have here on the left. Now once we reject the null hypothesis, so we have the low p-value, confidence intervals for the differences between each of the means. Remember there's 3 groups, sometimes there'll be 4 or 5, so that gets too large. So we don't calculate the confidence intervals for those. Once you reject, what we do is we conduct this 2-keys post-hoc test. So let's go to that. Sorry, compare means, one-way ANOVA, post-hoc, 2-key, no 2-keys B. Here it is. So this is one in the middle. Let's go with it on the left side here, so we're comparing the same thing. So what we look for is we look at full-time students compared to part-time students, full-time students compared to non-students. So we saw that that's where the biggest difference was between full-time students and non-students, and sure enough, it comes out as statistically significant. And it gives us the confidence interval for the difference. So we do get the confidence intervals here in the 2-keys test. In conclusion, we show that the samples represented, if we can show that the samples represented the population, we can see that full-time students spend significantly more money on junk food than non-students. And that would be practically significant because $17 a week is more. Plus, we have statistical significance. Very important. If we go back on the right side of the screen here, I want you to take a look. One of the things that we're assumptions that we're looking at is that the variances, standard deviations, for each of the groups must be equal. So standard deviation here is 14.8, 12.5, and 6.9. So we see we don't have standard deviations or variances. And the groups, each of the groups' distributions must be normal. Well, we can see this one has kind of a normal curve. This one maybe, and this one's really hard to tell. And so I gave ourselves a 1.5 out of 3. This has been a short, quick intro to analyzing data where there's one categorical and one measurement.